Good evening. My name is Anvesh, and today we'll be going over the solution set for week 7 assignment. The course is titled Interfacial Fluid Mechanics. So let's begin. So this is the week 7 assignment. Just a second. Sure. Okay, so this is week 7 assignment. So let's begin with the first question. The first question says the Froude number is defined as the ratio of which two forces? So this is the number we have seen in the falling jet. So if you remember, uh, so in the case of a falling jet, we encounter the Froude number, and the Froude number Fr is defined as inertia force to the gravity force. So the correct option here is B. Correct option is D. Um, Next question. In problems classified as free surface flows in the course, the gas is described as being passive. What does this mean? So, what does this mean? Uh, so we'll take a. We have looked at a thin film on a free surface, and we say that. So the fluid inside has a finite density and viscosity. Finite density and viscosity. But the gas above, when being said it's passive, we assume that the viscosity or is zero. The above gas is said to be passive when the viscosity of the gas is assumed to be zero. That is mu gas equal to zero. But the essentially we say that the gas is passive because the effects of the gas can be felt on the interface by virtue of the surface tension between the two fluids. That is, there can exist a gamma, which is gamma gas by gamma liquid. This can be present, and therefore this enters into the jump conditions. Therefore, we say that the upper gas is not entirely neglected but is considered to be passive. And this is a good enough approximation as for real cases like air, for example, air, the viscosity of air, the dynamic viscosity of air is around 1.27 into 10 to the power minus 5 Pascal second. So therefore, we can uh, choose to ignore this viscosity. So the correct option here is B. The B. The viscosity of the gas is assumed to be zero. Okay. We have the next question. Let's write down what it's. Consider a liquid jet emanating from a 5 mm radius. If the Weber number is 100 and Froude number is 5, what is the radius of the jet 30 mm from the nozzle? Given. Or not, is it? Sorry. The nozzle is 5 mm. Weber number is equals to 100. Froude number is equals to 5. Wait a second. Just Froude number is 5. Then it is asked find radius of radius of jet at 30 mm from the nozzle. That is r at Z equal to 30 into 10 to the power minus 3. Therefore, Z is equals to 10 to 10 to the power 3 meter. So we can say that the Weber number 1 by Weber number is equals to 10 power minus 3, which is small, which is in fact very small. Therefore, we know R by R naught is equals to 1 plus 2 by FR times Z by R naught to the power of minus 1 by 4. Let's get some space. So if we substitute the values, R is equals to R naught, which is 5 into 10 to the power minus 3 into 1 plus 2 by 5 into 30 into 10 to the power minus 3 by R naught, which is again 5 into 10 to the power of minus 3 whole to the power 1 by 4. So if we calculate this, we get, sorry, R is equals to 3.68 mm. Therefore, the correct option is 3.68. So the correct option here will be D. The radius R, the radius R will be equal to 2.6 mm. So going to the next question. I'll move this up. And then let's read the question. Consider the case of a journal bearing that works on the principle of lubrication theory. A key aspect of lubrication is that the film thickness decreases in the direction of flow. Based on the discussion on Based on the discussion on lubrication theory in the course, which of the below statements is correct? So, first option is viscous effects play a crucial role and they become important as one approaches the point of minimum thickness. So, the point of minimum thickness, if we work it out, epsilon, which is equals to h naught by L, goes to 0. That is, h naught goes to 0, which is the minimum thickness. This simply implies epsilon goes to 0. So we are talking about effects at when epsilon is 0. Then we say that the pressure depends on local thickness of the film and reaches a maximum as one approaches the point of minimum thickness. So we'll keep in mind that the minimum thickness is referred to as the condition when epsilon is tending towards 0. Then finally, the streamwise component of the velocity is significantly higher than the wall normal component. This simply implies that when we have a journal bearing, Here we see this is the streamwise component, and the perpendicular direction is the normal component. So now we have the momentum equation, which looks like so. And if we balance the forces, we get PC. PC is equals to mu u naught by L into 1 by epsilon square. So for epsilon limit, epsilon tends to 0, P tends to infinity. So the pressure approaches a maximum as the point of minimum thickness. So option B is correct. So if we look at the viscous terms, we see that the viscous terms are um, have have a term uh, so basically these are the viscous terms, and we see that if we take the epsilon inside, we have epsilon square by epsilon square del square u by del x square plus 1 by epsilon square del square u by del y square. Although this get cancelled, but this term is of the order is of the order 1 by epsilon square, which is very large. So again, the first first condition, viscous effects play a crucial role and they become more important as one approaches the point of minimum thickness. This also is true. Again, if we see the streamwise component of the velocity is significantly higher than the wall normal component. So again, we'll use the continuity equation. We know that u naught is equals to, sorry, v naught is equals to epsilon times u naught. So therefore, we can say that if u naught is along the flow, that is, if u naught is streamwise velocity component, then v naught is the normal component. Then as epsilon goes to 0, v naught also goes to 0. So all of the three options here are correct. Then the correct option is option D. So in this question, let us consider a thin uniform film of thickness h naught flowing down an inclined plane making an angle theta with the horizontal. Assuming the flow is fully developed, What is the expression for the flow rate? You can take nu to be the kinematic viscosity and g to be the acceleration due to gravity. Okay, so we have in the course we have looked at the uniform flow on an inclined plane. I'll So we have looked at this problem. In the course, the solution or the velocity profile has been derived for this flow, and we can say we can take the expression of velocity from there, which is equals to uy is equals to uy is equals to g sine theta nu h naught y minus y square by 2. So g sine theta by nu h naught y minus y square by 2. Let me check. H naught y minus y square by 2 g sine theta. Yes. So this is the expression we have. So to get the flow rate is given by velocity times area through which the velocity is flowing. So here we have uy dA, which is equals to taking a unit depth, we have dy, which then becomes 0 to h naught uy dy. Unit depth at unit, not unit depth, it is the width at unit width. It's one. Then we have 0 to h naught, 0 to h naught g sine theta by nu y h naught h naught y minus y square by 2. So we have, which is equals to g sine theta by nu h naught y square by 2 minus y cube by 6. This gives us 1 by 3 g sine theta by nu. So the volume flow rate, okay, so we missed out the, here it is 0, here it is h naught, so it will be h naught cube. So 1 by 3 g sine theta nu h naught cube. So that will be, the correct option will be A. Correct option is A, which is volume flow rate W is equals to 1 by 3 G sine theta by mu H naught Q. I'll take a quick break of 5 minutes here and I'll be back. Okay, now let's look at the sixth question. The sixth question is, consider the problem of a journal bearing and neglect the role of gravity. Neglect the role of gravity. If the housing and the shaft are perfectly concentric, which of the below statements are correct? So, if both the shafts are exactly concentric, the gap between the two, uh, the gap between the housing and the shaft is always equal and constant, which is equals to H naught. Then there will be generation of no lubrication pressure. So it's if the if the distance is always H naught, then there will be no lubrication pressures. So the correct answer is answer D. So we look at the next question. Consider a large block moving from left to right on a flat horizontal surface. If the thin film of lubricate if a thin film of lubricating oil is covered on the surface such that L and H are the characteristic lengths scales in the horizontal and vertical directions respectively, what is the appropriate scale for lubrication pressure? We know the so if we make the diagram. So this is the so this is a block and we have X and Y. So the characteristic length in X is L. Characteristic length in Y is H. Then we know we already know Mm, The scale for pressure is P P scales as mu U L. We know epsilon is given by H by L. This implies P scales as mu U L. Sorry, 1 second. Sorry, wait a second. Now it's working. Mu U L by H square. So the correct option is mu U L by H square. Okay, I forgot to present. Oh, okay, now it's visible. Again, I'll show you. Once we have substituted epsilon square with H square by L square, then it is mu U L by H square. So the correct option is C. Option C. And in the course, we have determined the shape and speed of a falling jet. Which of the below statement accurately describes the roles of gravity and surface tension effects? So we have seen that. So and we know from our analysis that in the falling jet, gravity accelerates the jet and surface tension decelerates. Sorry. So the correct option is option A. Gravity accelerates the jet and surface tension decelerates it. So now we have a combined question. So let's read out the question. A tightly fitting solid cylinder is able to move along the axis of a long vertical tube filled with oil of constant viscosity mu, which is being pumped upward at a volumetric flow rate Q. The tube has a small radius A plus h, where h is much smaller than A. The cylinder has a specific weight, which is W, and specific dimensions as shown in the figure, which is L, and the radius is A. Using the lubrication approximation, derive an expression for the volumetric flow rate Q required to keep the cylinder stationary. Assume that the pressure is uniform both above and below the cylinder. So, and the other question that is asked is, in the previous question, what is the pressure difference required to maintain the cylinder stationary? So we have both the question. So let's look at the solution. So first we have P inlet at the bottom and P exit at the top, and let's say we are looking at a region very close to, so the diagram will be, so let's take the axis to be here, as this can be simplified into a 2D problem, as it's symmetric about the axis. So we assume there to be symmetry, and this is a very thin gap. So it's a 2D problem. We'll simplify it as a 2D problem. So now we have the velocity field V is equals to U I cap plus V J cap. But the U component here is 0. Assumption 2D simplified problem setup to U is equals to 0, as there is only fluid motion in the vertical direction. And as of now, these are the assumptions. So we write the continuity equation. Del u by del x is plus del v by del y is equals to 0. This implies del v by del y is equals to 0. This implies v is only a function of y, and that is equal to a constant. V is only a function of y. Oh, sorry. V is only a function of x. X. So therefore, the third assumption is V. So we'll write the y momentum equation. Y momentum equation del v by del t plus u del v by del x plus v del v by del y is equals to minus del t by del y plus mu del square v by del x square plus del square v by del y square. So the terms that will go to 0 are v is not a function of t, therefore 0, u here is 0, and then v is not a function of y, so that is 0, and then v is not a function of y again, so this goes to 0. And then we have to write the pressure, the gravity, which is equals to rho g. So now our equation becomes del p by del, okay, I'll continue to write in black, del p by del y is equals to mu del square v by del x square. So plus rho g. So taking p dash is equals to p minus rho g, then del p by del y is equals to del p dash by del y. Therefore, we can take p minus p dash as the modified pressure. Taking that, our equation transforms into del p bar by del y is equals to mu del square v by del x square. Integrating twice, integrating twice with respect to x, we get v as a function of x, which is equals to 1 by 2 mu del p bar by del y into x square by x square plus c1x plus c2. So we need to find out the two constants of integration, c1 and c2. So we have Uh, we have the two boundary conditions, that is at the left boundary, which is equals to x equal to 0, um, v equal to 0, and at x equal to h, v equal to 0. So these are the boundary conditions. Sorry for the interruption. I'll just join again. Sorry for the interruption. Now we have the expression of v with two constants of integration c1 and c2. So we need to find the two constants by using the boundary condition. So the v equal to 0 when x equal to 0 gives 0 is equals to 0 0 plus 0 c1 plus c2. This implies c2 is equals to 0, and using the boundary condition v equal to 0 at at, at x is equals to h. So that is equals to v of h, which is equals to 0, is equals to 1 by 2 mu dp bar by dy h square plus c1h. So removing one h, this is equal to c1 is equals to minus 1 by 2 mu dp bar by dy into h. This implies v of x is equals to 1 by 2 mu dp bar by dy into x square minus hx. X. Okay. This we have gotten the velocity distribution in the vertical direction. Now we are interested in calculating the pressure difference in the problem. So pressure inlet and pressure outlet. Uh, Pressure inlet and pressure outlet. So we can say that on so there is shear stress. There is shear stress tau. There is weight acting down W, and there is a difference in pressure which is Pi minus PE. So writing down the FPD. So this is the free body diagram. Doing the force balance, we have W is equals to 2 pi, the length is L, the length 2 pi L into A, and then we have tau omega at x equal to 0, plus we have pi A square P Pi minus PE. So now we have tau, which is equals to 2 pi LA into minus of mu del V by del X, and that is evaluated at x equal to 0, plus pi A square Pi minus PE. So now we differentiate 2 pi LA into minus mu, dv by dx can be written as 1 by 2 mu del p bar by del y times 2x minus h. So plus pi a square pi minus pe x is equals to 0. So 0. This implies 2 pi L into A minus mu 1 by 2 mu del P bar by del Y minus H. So minus minus gets cancelled, and plus pi a square pi minus pe. So del we know del p bar by del y can be written as pi minus pe by L. Substituting, we get 2 pi a, mu gets cancelled, 2 pi a p pi minus pe L by L times h, so a get cancelled, plus pi a square pi minus pe. This implies pi pi minus pe into 2ah plus a square is equals to w. This implies pi minus pe is equals to w by pi a 2h by a. Therefore, the solution to the second question is uh, it is C. We have made a mistake. Yeah, we missed to cancel out this 2. Uh, we missed to cancel out this 2. If we cancel out this 2 here, then there won't be any 2. So the answer is C. Sorry for the mistake. There is no 2. So the answer is C. Correct option is C. Now we need to calculate the flow rate. So the flow rate. Let's first make the schematic. So an exaggerated view will look like So if we take a small channel, so if we take a small strip from between, we have the equation of volume flow rate W, volume flow rate Q is written as velocity times area through which it's flowing. So which is equals to U V of X into dA summation. Then we can write V of X into 2 pi x dx. So the area of the small strip is 2 pi x dx. So again we have, and then this strip is going from 0 to h in the coordinate system we have chosen. So if we do the calc, if we substitute v, which is equals to 1 by 2 mu dp bar by dy into x square minus x h 2 pi into x dx, and then we substitute p. We know uh, pi minus pe is equals to w by pi ah plus a square. This is the relation we got, and so if we divide this by L, we'll have an L here as well. So this is equals to del P bar by del Y. So now we have substituting substituting all of this back into the equation. This Q is equals to 0 to H 1 by 2 mu del P bar by del Y. Del P bar by del Y is given as W by pi AH plus A square L into x square minus x cube minus x square h dx, which is equals to 1 by 2 pi w plus a square L into x to the power 4 by 4 minus x to the power cube h by 3, 0 to h. 0 to h. Sorry, I switched the 2 pi. 2 pi comes in the numerator. So 2 pi. So this is equals to pi gets cancelled to w by a h plus a square into L times h to the power 4 by 12, h to the 4 by 12. So this is equals to 2w h to the power 4 by a h plus a square L to 12, which is 6, which is equals to w h to the power 4 by 6 a h plus a square L. If we look at the terms ah and a square, then ah is much smaller than a square. So then we can write the q. We can write q as uh, approximately equal to wh4 6 a square L. So the correct option for the question being okay. Again, sorry for the firstly. So firstly, one mu is kept here. So there's a mu. There's a mu, and W H cube 6 A by H plus A. Okay. So the error that I have made while doing this calculation, the calculation is that I've taken from this is A and this is A plus H, A plus H. So therefore the integration should grow from A to A plus H, A plus H. Similarly from A to A plus H. So all of the steps are same till this point, and here we need to substitute A plus H. So this is the mistake that I made in my calculation. So here we'll write it out again. Now it is 2 mu. So it is W by mu, W by mu times A into A plus H L into A plus H whole power 4 by 4 minus a plus h whole power cube h by 3 minus h a to the power 4 by 4 plus a to the power cube by h by 3. So if we now take common a from the first two terms, a common, which is equals to w by mu, a mu by a plus h into l, which is equals to a to the power 4 into 1 plus h by a to the power 4 into 4 minus a into a cube into 1 plus h by a cube by h into 3 minus a to the power 4 by 4 plus a cube h by 3. So if we do the linear approximation and write down the binomial sense, 4C0, 4C1, 4 factorial 1, 4C1, 4 factorial upon 4. So we'll complete the derivation. Uh, If we do the binomial expansion, then we have W by A mu A plus H into L into uh, A cube H 4 by 4 minus 3 A square H cube by 3, which then give the solution to be 6 mu H cubed A by L. I'll explain how this particular term comes in the next class, which is a third option, which is a B option. So, so the solution is Q. Q is equals to down. So this is the final solution. I'll explain the correct derivation of the um, volume flow rate exactly in the next class. So I'll end here. Okay. I'll end the class here. I'll see you in the next week. Okay. Thank you.